Varmt välkomna till Nobel Calling Stockholm som den här morgonen sänds ifrån Vetenskapsrådet. A warm welcome to all of you to Nobel Calling and to the Swedish Research Council. This week, the world's eyes are on Stockholm. It is a week when the importance of research, science, literature and peace are in focus. Between the 5th and 12th of October, this year's Nobel Prize winners are announced, starting today with a Nobel Prize in Physiology or Medicine. The Swedish Research Council is a government agency within the Ministry of Education and Research. The Council is the largest public funding body for research at Swedish universities and higher education institutions. We fund research and research infrastructures within all scientific disciplines. And we are also advisors to the government on research policy issues, and we have a national responsibility to coordinate communication about research and to fund activities and projects in that area. The events during Nobel Calling Stockholm are arranged by the Nobel Prize Museum in collaboration with a number of partners. My name is Helena Bornholm, and it's a great honor for me to open this exciting week with a lecture hosted by the Swedish Research Council. Our guest today became, at the age of 20, the youngest PhD in Swedish history. His research is the philosophy of mathematics, and for those of you who don't know what that is, you will soon find out. Welcome, Stefan Buijsman.
Hi, glad to be here.
Hi. How are you?
Good. How are you?
I'm fine. Actually, before you start telling about your research, I think people are curious. I mean, you're born in the Netherlands and you're sitting there right now, but they're also curious. I mean, how did you end up studying and doing research in Sweden?
Well, for me, when I finished my studies in the Netherlands, I was looking for a place to do further research. And the Swedish research climate was already back then really excellent. So there were much more opportunities in Sweden to do research and to work there, which is also why I'm still doing my research based in Sweden on a grant from the Swedish Research Council. And aside from that, the professors at Stockholm University were excellent. I wouldn't have been able to finish my PhD as quickly as I did without all the hours of help that they poured into it.
Before we hear Stefan's lecture, I will inform you that you are able to ask him questions in the chat on YouTube. And we also have a question for you. The winner will receive Stefan's book, Siffrorna i våra liv, published by Natur och Kultur. And you can send your answer to my colleague Magnus Boman, whose email address you will find in the chat. And the question is, why did ancient civilizations start using math? Alltså, varför började äldre civilisationer att använda matematik? Why did ancient civilizations start using math? So, if you listen carefully, we might get the answer. Please, I hand over to you now, Stefan.
Yeah, thanks. So I am going to be talking about mathematics, obviously. And I wanted to start with a really nice example from right now, something that we're able to do using mathematics, namely turning portraits like the Mona Lisa, as you can see here on the screen, into videos. And one of the reasons I picked this example is because it shows exactly the kind of role that mathematics takes. It's something we would be able to do. Of course, we could animate the Mona Lisa ourselves, but the math makes it much faster and much simpler. You don't need to know anything about animation in this case. All you need to do is you give the computer a picture and it turns it into a video just using math. So math, it is simplifying our life and it makes all of these usually very complex problems much more manageable. But rather than diving into there, I want to start first of all with a group of people who don't use math at all. It's not something you need to be using. And it's the people that you see here who aren't using it. They don't see any point, and they're called the pariah. They live in the Amazon rainforest, and one of the amazing things about them is that they don't have numbers whatsoever. So they wouldn't be able to say how many people are on this picture. They don't know how many children they have. But of course, they do know which children are theirs and which ones aren't. And one of the nice things about this culture, I think, is that despite this lack of mathematics, they still have really fulfilling and complex lives. One of the things they're able to do is trade. And they found a really cool solution for this. They just give away whatever they want to sell to a visiting trader. And then after they've done this, they start taking stuff, and they just keep taking something from this trader until he gets angry and protests that they've taken too much. And in this way, they're able to do trade. They still have a good sense of which traders are honest and which ones aren't, but they don't need to calculate anything. They don't use prices like we would do in a supermarket. They don't need to quantify things. And the reason that they don't need to do this is because our brain actually has a lot of capabilities already to deal with quantities without having to do any calculation. And we can run a quick experiment to show you this, where on the next slide, I'll show you two colors of dots. There will be blue ones and there'll be yellow ones. And even though I'm going to show the slide maybe for half a second, you'll still be able to see immediately, without counting, which one has more. So here we go. Now, you wouldn't need any additional work to figure out that there were more blue dots here than yellow ones. It's just something you see, and it's because of a part of your brain that works with these quantities without using mathematics. And it's what these pariah are using to figure out if they have enough food and to figure out how much they're giving away and how much they are getting back. The only thing is that this system in our brain is limited. It's quite helpful, but it's not as accurate as you might want it to be, because as soon as the numbers get closer together, you don't really see the difference as well anymore. So I have one more slide for you where the numbers of the blue and yellow dots are a bit closer together. And you'll see it's much trickier then to do the same thing. Here we go. Now, some of you might have guessed correctly here, but the thing is, it's going to be more guesswork. There were more blue dots in this case again, but it's much harder to tell. And it's because of that increased difficulty that eventually we started using mathematics. Now, before I'm going to give you a nice example of how we started doing that, I have one other bit of our brain that I want to talk about, namely something that allows us to work very precisely with small numbers. And even babies can do this. So the picture you see here is from an experiment where they're showing a baby two puppets on the left, and they're taking one away and then showing the final solution that there's one puppet left, as you would expect. And babies aren't surprised by this. But if instead you secretly place a third puppet behind the screen so that you are showing two puppets minus one is still two puppets, babies are going to be really surprised, and they'll keep looking at it and trying to understand where this magic new puppet is coming from. And researchers initially thought that this meant that babies can already do arithmetic. They can do 2 minus 1 is 1, and they can do 1 plus 1 is 2, and so on. Now, that turns out not to be quite right. The only thing babies are doing is that they're figuring out, oh, there's a puppet to my left and there's one to my right. The one to the right is gone, so there shouldn't be anything there. And one of the nice effects of this is that babies can only do this for up to 3 puppets, which means that if you put 4 of them in a bag, there's going to be some kind of weird overload in their brain, where if you do 4 minus 1, babies will think it's 0. So if you hide 4 puppets, you take one away, they will think there are no puppets left in the bag. Now, obviously, those are the kind of limitations that you don't want if you start to live together in larger groups. And so what we see across the world throughout history is that all the different ancient civilizations started to use mathematics, because the systems we have in our brain without symbols are just not precise enough. So as soon as people started living together in cities, they needed to gather taxes, they needed to know how much food was available, if there was enough food available for the population of those cities. And that's where we needed the additional precision and most of all the simplicity that mathematics was giving us. Now I picked the Incas in this case because they have figured this out in quite a unique way. Normally you would see symbols written on a piece of paper or on some clay, but the Incas didn't use an alphabet. They didn't have any form of writing. So instead they were using ropes. Those ropes work much the same as what you are used to. They have a decimal system. So you make up to 9 knots in one row. And if you want to make a 10th knot, you switch instead to the row in this image above it. And using those knots, then you can do calculations like you see here. But most of all, you can keep accounts. And those accounts look something like this. They become these really impressive looking necklaces almost of ropes, where every single rope stands for a number, and the colors give you some indication on what the numbers are counting. Now, that allowed them for very complex types of accounts. You could, for example, make a schematic here for a receipt from a supermarket, where a single rope would represent how much you have to pay, how much change you were getting. You could use red ropes for that kind of information. It will also show you how much taxes you had to pay, but just as well, how much you paid for all the individual items, whether you were paying for vegetables, for meat, or for clothing. All of this could be represented using these ropes with knots in them. Now, of course, that's going to be something very labor intensive. So they wouldn't do this for just any old trip to the supermarket, but they would use this for their taxes, for population counts, and for food storage, all for increased precision in their accounting. Now, you might wonder, and that's the kind of question that a philosopher would ask here, how is that possible? Why is it that mathematics allows us to do these things, that we get this additional precision and that we can apply it so widely? Because of course we can use it for accounts, but we can use it for weather forecasts just as well, or for making those videos of the Mona Lisa. What is it about mathematics that makes it so special? And I want to suggest that it's because mathematics studies patterns. Those patterns are everywhere around us in the world, and what mathematics does is it lets us focus just on those patterns, whether it's how much you have, where you would ignore what the food looks like exactly, how it's stacked into a heap, how much space it takes. The only thing you care about is how much there is of it, or whether it's for statistics, where what you want to know about, let's say, the current pandemic, is how fast the virus is spreading, how many people have gotten infected, and you want to get this as a quick overview, which gives you as much information you care about as possible in as clear a way as possible. And that's what mathematics allows us to do. It lets us focus on these patterns, abstracting away from the things that don't matter. Now, the only tricky thing here is that mathematics doesn't of itself know what the patterns are standing for. We have to apply it. We have to put the mathematics to use, and it can go wrong quite easily because it's something we have to do. We have to do the critical thinking here. And I can give you a nice example of where this can lead into a mistake. A recent study was looking at how old musicians are on average when they die. And I found a shocking difference between genres. On the one hand, jazz players were dying at a respectable 67, but rappers were shockingly enough dying on average when they were 27. Now, before you get all worried about this 40-year age gap and decide never to become a rapper, this difference is just a quirk from the way they were measuring their data, from how they were translating things into numbers. The problem here is that all the rappers who are going to be 70 are still alive. They could only count the people who had already died. And rap hasn't been around so long. So the people who did die from the rappers died young. If we wait another 40, 50 years, the averages are going to be just the same, or maybe a little bit different. But the 40-year difference here is just a mathematical quirk. And it's the result of these patterns not having any idea what they're counting. It's we who have to do the applying. And if we don't pay attention there, we might start believing all sorts of things. You might think, for example, that there's going to be a connection between Nicolas Cage on the one hand here, one of the famous actors, and swimming pools. Just because if you look at the math, there's going to be a shocking similarity between the number of films that Nicolas Cage was starring in and the number of people who are drowning by falling into a pool. So you might think now, if you just go by the numbers, well, maybe Nicolas Cage is getting his inspiration by throwing people into pools, or people have watched his movies and they get so desperate that they think, well, the best thing I can do now is fall into a pool and get it over with. But of course, there's no such connection in real life. This is just something that happens to happen. The math found a pattern, but the pattern doesn't mean anything, just as much as the pattern that math found between how much mozzarella cheese we are eating and how many civil engineers there are isn't based on anything in reality. But it's something that we need to be careful of. You can apply math, but the math doesn't really know what it's doing. So we have to do the thinking. And that works for statistics, but it works just as well for artificial intelligence, what I started with. So we saw that you can do lots of things with computers now, thanks to mathematics. And one of the things you can do is that you can get it to recognize objects on pictures. This is also, for example, how a Tesla manages to drive itself by recognizing when there is a pedestrian, what the traffic light is saying. So these kinds of systems are important to have, but they too rely on these kinds of patterns that they're looking for, which might not always be right. If you look at a picture here to the right, the computer thinks that instead of a dragonfly on this yellow shovel, it's looking at a banana because, well, bananas are yellow. So obviously, if you see something yellow, it should be a banana. Now, that's the kind of thinking a computer might still fall for. It doesn't always have to be so obvious. In the case here in the bottom right of a mushroom, which is sort of shaped like a nail, placed on a piece of wood, you might forgive it for thinking that it's looking at a nail, even though we would never make the same mistake. But the computer just as well makes a mistake on the candle to the left here, where there's really no clear reason why this would be a nail. It doesn't look like one. The colors are all wrong. But still, somewhere in the patterns this computer is using, it confused the two. And that gets tricky because it's hard for us to anticipate when these patterns are correct and when they're wrong. If you look at these pictures of turtles, a computer got it right only in the one picture you see on the right with a green border around it. That was recognized as a turtle. All of the other ones were classified as something completely different. And that's because of this weird background that these turtles are placed on. But it would be hard for you to guess what the computer might think here. I'll give you the answer. It was thinking that all of these pictures are showing guns, which of course is not something we would want a computer to do. We wouldn't want it to get all strange and defensive just because it's looking at a turtle placed on a bit of wood. But this is the kind of risks we're still running just because the mathematics these computers are running on doesn't know anything about the world. It's just applying patterns, and we have to do the thinking about whether those patterns are right. So to sum up, I want to say that math is a tool, a very, very useful tool, but not a perfect one. As we saw in the beginning, we started using mathematics to simplify tasks like administration, and it turns out that math is really, really good at simplifying a lot of things. Without it, we wouldn't be able to run the world that we have now, because it would be too complex. There's no way to deal with all the intricacies without having math around to simplify matters for us. But it often does simplify things in a way that could lead to results you don't want. It can depend on how you turn something into numbers, so how you measure things, how helpful mathematics is. And math can also lead you into mistakes because there's no understanding in the mathematics of what you're calculating. So it might confuse a turtle for a rifle, but it might also lead you into thinking that Nicolas Cage and swimming pools are somehow connected. So even though math simplifies things a lot by focusing on these patterns, we should keep thinking critically about it. And if anything, that's why even after school, when you might not be calculating anything yourself, it's important to be aware of something about mathematics. It has a lot of effect. A lot of decisions are made using it. And those decisions aren't automatically right just because they're mathematical. So it's up to us there to decide if the math is used correctly, if we approve, and that's how to use mathematics. Thanks.
Very much, Stefan. Actually, my colleagues and the whole film team laughed here in the room or in the studio when you told the example with Nicolas Cage and the swimming pools. That's really, really hilarious. Actually, just to connect to the things you just said, in an interview once you said that sometimes mathematics is used as an excuse to not be held accountable for online behavior, but ultimately the math is just a tool and we're responsible for how we're using it. What do you mean by that?
Yeah, so if you look at especially the large internet companies like Facebook, Google, Twitter, they might point to their algorithms to say, well, yes, we have these filter bubbles. We have all of these results of how our programs work. For example, that they have a lot of difficulty with filtering out hate speech because the mathematics doesn't understand when something is hate speech and when it isn't. And they might just say, well, it's the algorithm. It's not our fault. We can't help it that people are shown these ever more violent videos on YouTube or that they end up in these filter bubbles, but it's not a good excuse. They explicitly make the choice to use those algorithms. They could look for other algorithms. Admittedly, it's very hard to find ones that do a better job because it's very tricky to teach these computers something about what we are looking for. What content is appealing to people, what videos they want to watch next. So it's very difficult to find better algorithms, but that doesn't mean that you should just say, it's not our fault, it's the algorithms, and stop there.
So is it possible to explain in a simple way how the algorithms work? In Netflix, for instance?
Sure. Yes. So for these kinds of algorithms, the procedure they usually use is that they look at what you were watching. And it's the same on Facebook if you look at what kind of posts are you reacting to. And then they don't know what exactly the content is, but they can tell what other people who are watching the same thing were also watching. So they would simply recommend to you whatever the largest group of people who are watching the same kinds of things were also watching that you haven't seen yet. And of course, that's going to keep you in this kind of a bubble where everyone is watching the same thing and you might not be presented with a different point of view. So that's where these kinds of filter bubbles are coming from this mathematics, which is calculating what were the same people watching.
So do you think that people today, do we underestimate the power and relevance of math?
In a way, yes. So also I think with artificial intelligence, which is being used in more and more places. In the European Union, it's more heavily regulated, so that helps. But artificial intelligence is going to make more and more decisions. We are having fake news being automatically generated by computers. Computers are in some places making decisions about who to hire. So they're doing job interviews purely with a computer. And we have this kind of additional reach from mathematics and from algorithms into our life. And the researchers who are working on it are well aware. Lots of them are trying to find solutions, either to explain how these algorithms reach their decisions or to look at the ethics of applying them. But it can be easy to miss all of the different places where we run into mathematics in our life.
So give us a few more examples. There's not only Facebook or Netflix. I know we mentioned the coffee machine in the local store in
Yes.
the presentation of your lecture.
Exactly. So the coffee machine would use calculus, the one bit that everyone hates from school, to figure out what temperature the water should be at. It's calculating how fast the water is heating up, how long it should keep doing that, when it should stop heating the water. And all of that is happening using mathematics. But it's the same thing for your car when it's on cruise control, which is calculating, should I increase my speed? Is there a car nearby which I should pay attention to? Tesla is doing this in particular with the self-driving cars. But it's not just those parts. One of the interesting things about the pandemic is that it showed, for example, how heavily dependent our warehouses and our supply chains are on mathematics and on finding the same patterns. So when the pandemic started, people started ordering different things in different numbers. And all of the mathematics that was based on making sure that the right products get in the right places stopped working because they weren't used to the situation that we were suddenly presenting them with. They got confused and they thought, well, no one would want this many masks. We don't really need to order that many. And they started making mistakes because the mathematics was presented with a completely new situation and it just couldn't deal. We had to manually readjust those supply lines to make sure that everything got to the right place. And in these situations too, behind the scenes, there is a lot of mathematics.
So for you, being a researcher, is the pandemic now is a very interesting period to study in terms of mathematics and what happens?
Yes, so I don't do a lot of that myself because the research I'm currently doing is focused more on how we learn mathematics. So on how children start to count and what everything that we know about how this learning process goes, what that means for philosophy and our wider understanding of how we work with mathematics. But it's something I would want to continue on more in the near future, to look at artificial intelligence and to see how we might best explain how these systems reach their decisions. And if we can better explain their decisions, then we might also be able to anticipate these kinds of situations in the pandemic. So it's going to be a very, very interesting case for researchers everywhere to study and to see how these computer systems and how this mathematics was reacting to it and where things failed.
So talking about how children learn mathematics, actually you focus basically on two kind of questions in your research. That's why can we live without mathematics, and what does that mathematics do for us? How did you get interested in those two questions? What was it like when you went to school when you were younger? And
yes. No, I think when I was in school, I didn't really like mathematics. I wasn't particularly good at it. In high school, my grades were average at best in mathematics. And it wasn't really until university when I was doing philosophy that I started to like doing mathematics. And I think what I was missing there to a large extent was some kind of explanation on what we're doing and why we're doing it. And I think that shift in thinking for me made me want to research, okay, but how can we make this better? And as a researcher, of course, you want to understand. I think it's good to start not immediately with how can we make things better, but rather with the question, okay, how do people actually learn mathematics? What are the things that we should be focusing on? So to understand the learning process and then try to improve it based on a better understanding of how it works. So that's where my research started off. I was interested in, from a philosophical perspective, how this actually worked and how we could connect it to the philosophical theories that we have. So there are lots of philosophical theories about how you learn mathematics, how it's possible to learn something about these really abstract numbers. And I wanted to connect that to the empirical research that we have on how children actually start to learn mathematics and how adults are doing this.
Do children?
So it started, I think.
Do children and grown up do we learn in different ways? I mean, if you haven't studied math when you were younger, is it harder when you become adult or older?
Yes, I think so. So if you look at these indigenous tribes, like the Pariah, they tried to teach them mathematics because they asked for it to the researchers that were visiting the villages. And they did learn a little bit of mathematics, but most of the time when they were in math class, they would refuse to answer the question, or they would think that, well, there can't be just a single correct solution to everything. So if someone would ask them, what is 1 + 1? They might just answer by saying a random number, or they might be annoyed by having to redo the same exercises over and over and just start telling some story about what they were doing during their day. And so after a few months, the researcher got frustrated. He was asking them, well, why are you showing up if you're not going to take this seriously? And the main answer why they were coming to these lectures was that it was a nice way to see everyone, and the researcher was making popcorn. And they were interested in having more and more popcorn. So for them, I think it was mostly that they weren't particularly interested in doing mathematics. They didn't have this additional value for doing mathematics. But the learning process wouldn't have been any different. Of course, it's, like we know, easier to learn some things when you're a child. It's easier to learn a new language when you're 4 compared to when you're 50. So in that sense, some things are going to be harder when you're older, but the basic procedure is going to be the same as far as we know.
We had a question from one in the audience, and I'll see. I watch my colleague here to see if I quote it correctly. It was like, I've heard that the number of math students are decreasing in Sweden. Why do you think it's like that?
Yeah, I think mathematics in general, and in the Netherlands too, one of the things I think is difficult about it in the way we're teaching it in school now is that there's a lot of focus on just calculating. So the emphasis is not so much on understanding and on looking at what you're studying and why you're studying it, why mathematics works so well. And of course, if the only thing you're doing is just brutal calculation where you have to compute one sum after another, it's going to be very difficult to find it interesting and fun to do. So I would think that that kind of approach, which we see in lots and lots of places, is going to lead to fewer people wanting to study mathematics because they don't see why you would want to, what the interesting thing about mathematics is.
Okay, we have another question. The assumptions we put into the math models are crucial for accurate precision. Is there a connection then between mathematical philosophy and behavioral science, or is this outside of the scope?
Well, I think it's a good question. The assumptions are crucial, and I think mathematical philosophy works on this to some extent. So what we are looking for in our research partly is how mathematics can be applied and why it can be applied as helpfully as it is. So we are looking at the broad picture of how this application works, what kind of features of the application make it successful and which ones make it less successful. Philosophy doesn't usually look at any particular predictions. So the philosophy itself isn't going to give you a good guide on what to look for in the assumptions that might lead you astray. But it does focus on the kind of critical thinking you need for that. And I think their behavioral science too might teach you something about the kind of assumptions we might be making, which might not be appropriate, or were the kind of pitfalls that we often are presented with. So I do think that both can be very relevant for trying to get a better application of mathematics, but they're approaching it in different ways.
So we told in the beginning that you have a grant from the Swedish Research Council now. Tell us what that project is about.
Yeah, so the research project there is to focus on, like I said a little earlier, how we are learning mathematics. And what I'm doing is that I am trying to formulate a more philosophical theory on how this learning goes, how we are using mathematics, and specifically in connection with all the different empirical results that we have. So I work together with psychologists and mathematics education researchers quite a bit to try to do the theoretical part of their work from a philosophical perspective. So for example, there's a large debate in psychology about what it is about about the brain that allows you to see those differences between different numbers of dots, like we had in the experiment at the very beginning of my presentation. We want to know how that system works. What is it looking at? In what way is it processing the information that it's getting? And one of the things I'm doing is that together with those psychologists, we're formulating theories that someone else can then test. And it's the same thing with mathematics education, where they have theories about how students in classrooms are learning mathematics. And a part of those theories very often is a philosophical perspective on what is it that these students are going to be learning, what is mathematics, and in what way do you have to learn something about those mathematical objects like numbers. And so what I do together with those researchers is that I work on those theories to see what the best perspective is to take on what mathematics is and how we learn it in a general sense.
So what is it like to collaborate with research from other disciplines? I mean, do you always speak, you don't the same language, or are there situations where you don't understand each other? Because
yeah,
you have
definitely. Especially in the beginning, you run into communication issues quite a lot. I think mathematics education in this case was the trickiest discipline to communicate with, because we, in philosophy, we use a certain set of words about mathematics. So we might talk about objects, for example, where I would just mean specific numbers or triangles or circles. But in mathematics, in mathematics education, when they're talking about objects, they could just as well mean problems or solutions, exercises the students are doing. And I think it took us quite a while to figure out all of these different words that we were using and how we were using them differently. So it took us, at least in the beginning, several hours of just gesturing and drawing diagrams to show how the different words fit together, until finally you get a bit of an idea on how these people are talking about mathematics. And then in the end, it turns out that they might think about it in much the same way as we do in philosophy. It's just that they express those thoughts very differently.
Actually, if we go back to the things you told about the history and about you told us about people that doesn't really use mathematics. I mean, the world is becoming more global and complex. Is it possible that it will continue like this for those tribes or groups of people, or do you think there will be a need for mathematics all over the world in the future?
I think with these indigenous groups, as long as they're in the situation they're in now, which is very isolated in the rainforest, which is providing them enough food and which allows them to continue with the lifestyle they've had for millennia, then it's okay. They might continue in this way. The real threat for those people, whether it's in the Amazon or in Papua New Guinea, where that we have another couple of these tribes who use very little mathematics, is that we have to deal with global warming and changing environments. So the lifestyle that they have might, in the end, have to disappear because of our actions, not because of anything they do or because they want to change anything, but because the environment is going to change. And in that case, if at some point they're forced into our society, then they have to start learning mathematics. Because the way we've obviously set things up is that you need to know something about numbers. Otherwise, you can't do anything, really. You can't do your taxes. You can't do shopping in the supermarket. So the real danger to their lifestyle is not anything they might choose, because they're very happy with the way they're living now, but that our society might encroach on the spaces that they're inhabiting. And if that happens, they will have to change.
So what do you think about the use of mathematics in the future for our part of the world? Talking about artificial intelligence, for example, what will be possible using maths?
Yeah, I think there's going to be a lot of possibilities there. Artificial intelligence, as everyone knows, is getting better and better. On the other hand, it's not going quite as quickly as the media might sometimes suggest. So one of the really, really difficult parts about using mathematics and artificial intelligence in particular is that the mathematics doesn't understand what it's talking about. So artificial intelligence, if it's writing an article, it doesn't understand what it's saying. So a computer wouldn't see any problems with talking about, let's say, a wood fire underwater or a unicorn with 3 horns. It wouldn't see any contradictions there because it doesn't know the meaning of the words it's using. And it's the same thing for analyzing pictures or making these videos. It's very challenging to get the computers to approximate our behavior because we can't just explain it to the computer in the way that we think about it. So as a result, the good news is that I expect a lot of the jobs that we have now to survive for quite a while, because as long as there's some kind of understanding you need to do your job of what everything means, how things fit together into society, or what, say, the words that you're writing mean, that's something that a computer won't be able to take over. And you see this, for example, also with Facebook and Twitter and so on, who have to employ thousands of people to look at posts and to check whether those posts are politically correct or whether they should be removed. because the kind of understanding you need to figure out if something is ethically acceptable or not is not something we can put into a computer at any point. So as a result, there are definitely limitations to what the current technologies can do. But on the other hand, they are simplifying a lot of tasks that we find the most annoying. They're really repetitive tasks where you don't need to know anything about the wider world, like sending a product from one place to another because it's requested, or finding, let's say, the most optimal route. Those kinds of things can be digitized, and it can lead to, I think, really wonderful applications. So one thing they can do now is that they can use satellite images to scan the seas 24/7 to look for illegal fishing, where a computer would just analyze the pictures over and over to look for any signs of illegal fishing boats. And the same thing you could do in the rainforest for illegal logging, where you track automatically where something is going wrong. And that kind of 24/7 total surveillance is something you can only do with computers. It's something you have to be careful with, obviously, because we don't want to have surveillance of ourselves. But in certain cases, like with illegal fishing, it's something that might actually help.
So you're doing research on how young people learn math, but I mean, you also have knowledge about, I mean, how math is used and how we are affected by the fact that, I mean, it's part of our lives. Do, for example, for instance, other companies or other areas are interested in your research? Like
yes, well, yes. So especially now that I'm working a bit more on artificial intelligence, and I'm hoping to continue that research into the future after my current project is over. There is more of a question of, okay, what is this artificial intelligence capable of? How should we be using it? How can we use it? And that's something that for a lot of companies too is relevant. So this is a project I started fairly recently. Last June, I published a popular science book about it in Dutch in the Netherlands. We'll have to see if it comes to Sweden. We're not entirely sure yet, but that's where
is it available in English?
Work started for me.
Sorry, is your book, the new book, available in English?
No, it's going to be published in English, but translations take usually a year or so.
Okay.
So there's going to be a bit of a wait, unfortunately. But since then, I've been talking more and more to companies also about how they are using AI, and talking to AI companies to ask what kind of problems they are running into. So that kind of research is definitely getting a lot of attention. And it's nice to see also at the Institute for Future Studies where I work, that they have a whole group of researchers there working on these kinds of ethical questions of AI and interacting in Sweden with companies as well.
So we're soon at the end of this morning session, but going back to the question we asked in the beginning, why did ancient civilizations use math? What is the answer? You've already said it, but
yeah, I think yes, exactly. I think the answer really is that for them, mathematics simplified their accounting. It wouldn't be possible to live in the cities that they lived in, even though they were, for our understanding, still very small cities with maybe 10,000 people or so. They wouldn't have managed without some kind of system to keep track of how much food there was, how much taxes the government was getting, what the trade balances were like. Without that kind of system, they wouldn't have been able to survive in those large groups. So they invented mathematics. And all these different civilizations did so independently and in their own way. So you see very different looking systems from China to Egypt to the Incas, but all with the same goal, and all of them using the same numbers, just in a different method.
And actually we have a winner. It's Sofie Verkö, who will receive your book. Siffrorna i våra liv, hur vi använder matematik utan att räkna. So congrats to you. Before we say goodbye, Stefan, it's the Nobel week coming up. What are you doing this week, and which one of the Nobel prizes are you looking forward to hear about?
I'm obviously following the research actively. I think it's always a lot of fun to hear all these different research areas and how they're being used to make the world a better place. One of the Nobel Prizes I think I usually look forward to is the one in literature, funnily enough, because aside from my own research, I spend most of my time reading novels. So hearing about all these different authors and what kind of work they're doing and the very different approach they're taking to describing our human experiences is something I always enjoy. So
do you have any guesses for this year's?
No, it's too hard in that sense. The Nobel Prizes are, they manage to surprise, I think, and that's a nice thing that they bring also in the attention research, which normally you wouldn't hear about.
Okay. Thank you very much, Stefan, for joining us this morning. Looking forward to hear more about your research in the future, especially the granted project you have with the Swedish Research Council and the Institute for Future Studies. Have a nice week in the Netherlands.
Have a nice week in Sweden.
Bye.
Bye.
And to you in the audience, I would like to say thank you for watching us this morning. But before you leave, I hope to meet you again on Thursday morning at 9 o'clock. You will meet Anna Rising, who is a researcher at Karolinska Institutet, and she's doing research in stem cells research, and she's leading a project where they create cobweb fibers by artificial means. So don't miss that. Very welcome Thursday morning, and bye, Stefan Buijsman and all of you in the audience. Have a nice week.